The following material is for informational purposes only. It is not intended to be and should not be used as a guide for conducting an actual dredging operation. Dredging is a highly regulated and potentially dangerous activity and should only be conducted by a qualified master, crew, and vessel licensed pursuant to and operating in conformity with all applicable federal, state, and local laws and regulations.
Hello, my name is Tony Dow. I'm going to talk to you about our Dredge calculator worksheet. It's just a tool, but we're going to go through it to make it some sense for you. There's a couple things it does. Weak link calculator. We also have the dredge operating tension details. We also have the max dredge calculator, and there's some instructions on there. You can go through the instructions. They kind of run you through that. You talk to MARSSAM. We'll help you go through this. We'll get on a Zoom and share the screen and go through this with you. But right now we're going to go through the section on how you determine what strength for your bolt. And this is kind of an old style where we actually have a bolt. The new style, we have a pin. The new style is going to be vastly superior. It'll hold the tolerances of the strength variability in the pins closer, which will help you have more consistent results on the bottom. So the first part up here, any cell in yellow, that's a value you input. The assigned brake load, the 3x19 9/16 trawl wire, 32,000 is kind of what it comes from the factory at. But with testing on your ship and whatnot, you might not have all of that left. It might be a representative sample, and it breaks at less than that. So that's the assigned brake load. So you enter your assigned brake load in there, 29.5. It's already entered there. We can play with these values later so you can see how that changes. The UNOLS approved safety factor. Usually this value here is 2. On this dredging cruise, we've asked for a waiver. We asked for a waiver for 1.5, and you'll see why down here later. I'll leave it at 2 right now, and then we'll work through it and change it. So the safe working load, that's derived from the factor of safety. Right now, our safe working load is 14,750 pounds. The next line down, the weight of wire in water, 1.4 pounds per meter. There's a little bit more slop in there, which doesn't matter too much, except once you get 8,000 meters out, it starts to add another 30, 40 pounds. The next line down, anticipated deployment depth. So if you're going to work through this and you want to figure out what value to have for your weak link that's going to break and free your dredge on the bottom and keep your wire from exceeding the yield strength of the wire, which is very important. So you put in your anticipated deployment depth. We've got 3,000. Let's try 3,500. And then your next line down, your wire scope. This is basically the difference between the multi-beam depth and the amount of payout you have. It's going to take a little bit more wire to get there than just exactly what the depth is. Sometimes your winch scope changes if your payout meter wheel is gotten messed up. There's reasons why this can be massively out of whack. It should be in the 1.2, 1.3 range. If there's a lot of current on the bottom, if you're operating in an area where there's a 3-knot current along the seabed, that's going to pull your package out. Some of you might have seen this when you're doing a deep water stationary CTD cast. You might have 4,000 meters of depth, and you might be at 3,700 meters on the CTD, and it's still not going down, as noted by the pressure depth on the CTD. And then you might have 4,500 meters on the payout of the CTD, yet it's still not getting to the bottom. That's a situation where you know there's a lot of current on the bottom. For here, with the rock dredge, it's a pretty good, solid, heavy bottom. We're going to use 1.3. It's somewhere usually between 1.2, 1.3, maybe 1.18. So this then, below that, the weight of wire underwater, that's computed from your anticipated deployment depth and your wire limit. You can click on the cells and you can see the formula that's in use there. From that, you get to the next line down, the anticipated seafloor working tension. So that's all you got left. At that sea state, with that break strength, you've only got 8,361 pounds left. Pretty well, you only got 8,000 pounds left to work with. At you talk to Dan Fernari, he wants to pull on some rocks at 18,000 pounds, so you're about 10,000 pounds shy here. So this is kind of a bummer. You're not going to get much work done down there. But anyway, we'll just keep working through it. So from that, because there's a slight variation in all the different strengths, the tightness of these, which we're trying to address by machining bolts and pins for that, this maximum weak link break strength is computed, and there's a tiny little bit of slop in there, this 1.1 in the formula up here. You can take that out if you want. But that's where you would not want to exceed the 8,360 pounds. And really, if you look at that, that's only about 600 pounds. So if you're fussing over 600 pounds, you're kind of not really able to dredge anyways. In the old days, you couldn't make a weak link on board. You were stuck with whatever was in the bag and the little kit that you had. So you find the closest weak link below this value, so the 7,722 value, the closest weak link you found was 6,400 pounds. So if you enter that value in here, maybe you found a 600, 800 pounds, so we'll enter that in. And then you have a side link. The side link is on the side of the dredge. You want one side to break off, and if it's stuck, maybe that'll break off and help get it unstuck. So that number is a little less than half, and that's computed here. There again, if you have to go find a link that you might not have been able to make at sea, the closest one you got was 2,300. So right there you can see you could have pulled up to 3,400 on the side link, but the closest one you found was 2,300. So you just lost another 1,000 pounds of overhead. Yet another reason why you want to be able to standardize and make links at sea. We have to thank Dan Fernari for that, because that's been a long time coming, and we're addressing that now finally. Anyway, so at that point, you've got these two numbers that have been derived for you, the maximum main weak link break strength and the maximum side weak link break strength. And hopefully you can get really close to them when you do your selection. The chosen side link, 2,300. It just so happens that this aluminum bolt is about a 2,200 pound weak link. So I'm going to put that 22 in there. And what that'll do is you're pulling on half of the bridle with a chain bridle type dredge, not a bale type dredge. You never quite know if one chain or the other is taking all the load. It might be that you're hung up on a rock next to one side of the dredge that didn't have the weak link on it. So in that situation, the side one might not break, and you might break the other one first, which is too bad. Then if that happens, then you end up at the sort of the safety purse cable break strength, which does work very rarely. We have a photograph of it. We can show you that. So that's kind of the way you work through this worksheet to choose the values for your weak links. When you're actually running the dredge, all that stuff goes away, and here you are in your operating tension details. There could be some opportunistic science that you're doing. You've attached a mapper on the wire which sniffs for hot spots or different chemical traces in the water. So if you've done that, here's a little number. You can just enter that here as a way to remind yourself, mostly to remind the winch operator not to two-block the instrument when you're coming aboard. If you're using a pinger or a beacon, that's usually below the mapper, so you can enter that number here also as a way to remind yourself. If you're flying the dredge and you didn't quite get to the spot, or there was something wrong with the multi-beam or whatnot, or you're on the bottom, you know you're on the bottom, you can see that from the tension, this is the number you're working with. So enter your number in here. You're actually at, say, 6430. That's how many meters of wire you've got out right now. So then this next line computates the current weight of wire in water, 9,000 pounds. This dynamic loading, that's accounting for the sea state and swell. And when you're picking the weak link, you're not usually accounting for that, but if you decide to go dredging on a really rough day, that number is going to be really high. These next lines down from that, the expected side weak link break tension, this is what you're going to see is going to break off. And then the next number, you can see how it's turned red, the 15,829 expected main weak link break tension. I mean, we've already broken this dredge off. And this number over here, if this turns red, you've already exceeded the safe working load. This 23,863. We're we're already broken. So this whole little academic exercise didn't work. So right up here, you can see if that works for you. You can go back to 4,500 meters. We're still in the red over here. I think, though, we started with a factor of safety of 2. So this is why you want to go and have a factor of safety and ask for the waiver, put a factor of safety of 1.5 in. So now, this next number, instead of 15,000 pounds, now it's 19,067 pounds. Weight of wire stays the same. Anticipated deployment depth stays the same. All these other things stay the same. We go back down to our operating tensions. Lo and behold, we're still in the red. So even with the factor of safety 2, with this kind of high heavy-duty sea state, you can't dredge that day. Still can't dredge. Oops, wrong cell. D8, D12 plus 8, 5. 3,500. Still running out. We just got down to an area here. Now this little box here turned to green. That's kind of like a clue for you. Our expected weak link side maximum 3,000. Maximum main weak link is 9,000. Back up here, you go back. We chose the weak link value of 6,800. That was too much. We should have put in a 4,500 weak link. Then everything's okay. We go one more over. Here's just a little depth calculator. So this calculator, if you're sitting there and you want to decide what kind of sea state and how deep you can go, this multiplier number here, cell D4, you have to have at least a 1 there, but it's going to take a little bit more wire to get to the seabed than the 1. So we'll do like 1.18. That's a good number that you've gotten from experience from previous dredges. Total tension swings as seen on your winch monitoring. Let's just say it's utterly, absolutely flat calm, which is pretty much an impossibility at sea. So we'll put a 0 there. And the weight of the dredge, when the dredge is on the bottom, it's in fact 0. But the minute the dredge comes off, now it's on the A-frame and on the tension load. So this is sort of an academic number when you're in shallower water. You don't really have to worry about this. But when you're in really deep water, the second that dredge comes off, you don't want to break it off. So let's just add the weight of the dredge, 500 pounds in water. And there's a pinger and there's a mapper and whatnot. So now how hard do you want to pull on rocks? How much do you think you need to get a rock to break off down there? Let's say 4,000 pounds. Is that worth it? To put 4,000 pounds in there. Now what you have is the deepest that you can go is 9,000 meters, and you're only pulling 4,000 pounds. But if you have any sea state at all, which is always the case, let's say you've got 6,000 pound tension swings, put that in there. Now you're down to 6,000 meters, just like that, with a normal sort of sea state on the ocean. If it's a rough day, you got 7,500. Now you're down to 5,000 meters. If it's rough, the other thing that happens is you might be a little more scope. Now you're down to 4,800 meters. If you want to pull really hard, you think the bottom, you need to pull like 8,000 pounds, 6,000 pounds. Let's say you're going to compromise and go 6,500 pounds. Now you're at 3,500 meters is all you can pull. So that's how this little tool works over here. And there's the link. And there's the instructions. There's a little link right here in this little instruction box that brings the Appendix A winch and wire workshop. You should know this, intimately know this. We have another little video that describes how wink links work. This, by the way, even though it has a single bolt, one hole, this is called a double shear. Double shear does not mean 2 holes. Double shear means a double shear plane. There's this shear plane and that shear plane. That would be a single shear plane. That's a double shear plane. The other thing is be cognizant of your shackles. your hammer locks, which are stronger, and your main oval link. This is kind of a living document, and a lot of people have added to it. It's been going around the fleet for a while. This safety factor, this multiplier, some people don't want to use that. Some people want to do it a different way. Weight of wire and water, that pretty well stays the same, but if you were going to use a different, like a synthetic tension member, for instance, we'll just show you, if you use a synthetic tension member, there's basically 0 weight of wire and water for all practical purposes. Then all these numbers change, and if there's 0 weight of wire and water, then you can go to the bottom and work really well. Look at your main weak link now becomes 19,667 pounds because there's no weight of the wire to deal with. So you've got all that tension at the seabed you can work with, minus the weight of your dredge. This will be updated as we can. This video might not match the latest one, but when we get to it, we'll make a new video. And if you have other ideas for this and want to talk about it, we'd love to hear it.